CR 4101, 5101. This is lecture 25. Welcome. I am going to go over one minor question that we had, and this will be helpful for preparation for the final exam. And I've already answered questions on the final exam. And it is on requirements. So let me say, or let's say, for example, you have in your you have a discussion about, I don't know, a snack food machine, right? And I ask you to write requirements. An example of a requirement could be, 1, the machine shall accept 5-cent, 10-cent, 25-cent, and $1 coins. Keyword here is shall. 2, the machine shall have a device to detect if the structure is being shaken, not stirred, or tipped.
I had something like that on my midterm, and I had to explain it off, and it was wrote how with a question mark.
And as always, when things are graded, make sure to talk to the grader first, and if you're not happy with that, then come see me.
Okay.
All right? That is in the syllabus. The semester is not over yet. Go run. Let's see, what's another requirement? Somebody give me one.
Change, return.
Leave my change.
The machine shall have the ability to return all coins inserted when a change return button is pressed. Shall. You want to make sure that your requirements are fairly succinct. You want to make sure that they identify functionality. Now, did I talk about systems engineering in this class?
A lecture.
The entire or just a little part?
Half a lecture.
Did I talk about organizing your requirements in different functional areas? All right, I must be thinking about my robotics class where I actually talk about systems engineering, as well as my advanced embedded class where I talk about systems engineering. So I'm not making you do that. That's an example, all right? Any other questions about requirements? All right, let's look at and continue with the transparencies. Just as an FYI, this is, I'm only at 20 of 64. I wonder how much I'm going to be able to get through. Well, I'll tell you what. We did this example here, so I'll just go through it a little bit more detail, and then we can, or we'll look at the example that I have, and then we'll be able to perhaps even go into it in a little bit more detail. So, I had this example, and this is very similar to what we see here. where, oh, when you know. It's kind of like a quiz. All right. Fill in the table below to show which task the processor will execute and when, as well as scheduler table contents. Assume that timer tick interrupts occur every 1 millisecond. So now we know what n is. And all tasks take 1.2 milliseconds to complete. All right? So the first thing we say is, what is this amount of time right here? 1 millisecond. If something starts running at this point in time, how long will it take? So it'll go into the next one, right?
Yeah.
A, B, and C are 2, 4, and 5 respectively. That's the initial value, right? So I'll just keep this in mind. The initial value for A is 2 for the timer. It is 4, for this task, and it is 5 for this task. Okay? That's the frequency of how often each one of those tasks will run. That's the initial timer value. So we're going to start right before time n, and that's the value, and nothing was running then. So what we're going to identify is when the timer tick goes from 1 to 0, that means it's going to run. So let's take a look at an example. At time n, our round robin says that this will go to which value? 1. This value will go to 2. This value will go to 0. When it's at 0, it means run. So we need to make sure that we identify that that is going to run. By the way, everything else is going to be 0, so I'm not going to enter it in because it makes it a little bit messy. Oh, by the way, enabled, assume that's going to be 1 all the way. We're just going to keep on running this. By the way, if in our round robin we say if it counts down to 0, then we reset it to its original frequency. Are we going to keep 0 in this location? No, it'll go to 5. And by the way, what activity will go on? Well, obviously we're going to run C during this time. And C will take this amount of time right here. I like colors. All right, we're all done, right? By the way, just for grid, I want to put 0 here and put 0 here. By the way, after it starts running, the results here will go to 0. Yes, sir?
Wouldn't it stay 0 for 1 tick and then go to 5?
No. Our algorithm is such that when it encounters a 0, then it says time to schedule. And that will cause me to change the timer from 0 to 5. And at the same time, I change run from 0 to 1.
Okay.
Then in the process of starting up running, then I change it from 1 to 0. Because I addressed it immediately.
So, is the correct answer in that run block 0 or 1 marked out with 0?
What would be the correct one? The eventual correct one would be 5 and 0. But to show your knowledge of all this, it would be really, and for possible partial credit, I would say 0 crossed out 5 and 1 crossed out 0.
I still don't know how he got 3 to 2 and 1.
All right, so at time n plus 1, what is going to happen? This goes from what? 1 to 0.
No, this is just
So
the time.
it gets crossed out, it gets set back to 2.
This is the starting.
Okay, so how'd you
This is set to
because
1.
it's 1.
All right?
Okay.
And then back to 0.
Hold on. So, what does this go to?
1,
2 followed by 1. It's not running.
4,
What is this? 4, 0. Now, as soon as activity C is completed running, our round robin algorithm will say, hey, it's time for this one to run, which is A. And so it'll schedule A during this 1.2 milliseconds, right? And this was, remember, this one was 1.2 milliseconds. And so in here, you can say, all right, this gets changed to,
no,
oops, sorry, wrong line.
Double cross.
Now, what happens at
One
this
minus
time?
2.
1,
2 goes to 1. At this time, 1 goes to
0,
0,
to 4,
goes back to 4.
goes to 1.
I'm going to do an X instead of just a slash. This goes to, will this go to 1?
Yes.
Yes.
All right. This goes to
3,
3. This goes to 0.
I have no idea what happened.
And was this, oh, this was 0 as well, right? So after this is done running,
Then B.
we notice that, oh yeah, this is going to take some time too. And again, this is 1.2 milliseconds. This is B's going to run. And this will change from 1 to 0. So n plus 1 now, this is going to change to
0,
0.
to 2,
So we change this to 2 because that is scheduled for 1. This goes to
3,
3. This goes to 2. And during this time, we notice that we need to run task A again. Which means that this will start, it will be changed to 0. Now we look at this, moves to 1, 3 goes to 2, 2 goes to 1, nothing is scheduled, so this is actually blank time, right? So what happens at the next step? 1 goes to,
0,
which then gets to 2, this changes to 1. This goes to 1, nothing is scheduled. This goes to 0, which then gets changed to
5,
5. So it's scheduled for 1. Now, who runs?
A.
Yeah.
That's a higher priority. A.
Who said B back there? Who's a smart aleck who said B?
Okay, why did A run this time?
So it says that assume task A has the highest priority, which means A will
No,
run.
yeah, this time I get this time, but last time,
Let's say
why
1.
did A run last time?
It runs exactly after.
Okay.
So it wouldn't be good.
Well, with the 0.2 for 8, because it was 4, 1.2, which was 14 milliseconds.
Easy enough?
Why is there a big Why is this break?
So why did we take A first? Well, you understand, first of all, one thing I want to note. So right here at this point in time, there is idle time, right? So nothing is going on, nothing is scheduled. So at this point, when A is scheduled to run, this changes to 0. C can't get to run yet. So let's look at the next time. This is now, this changes to 1. This changes to still 0. This goes to 0. 4 because this goes to 1. This is at 4 and it starts still at 1. So what executes at this time? Pardon me? Run is still, right here, run is still 1 because it didn't get to execute yet.
But B has priority, so B is it.
Now B has priority. So B will run for 1.2 milliseconds. And because of this, B will be set back to 0. And we'll do 1 or 2 more because otherwise this is getting really long. Alrighty, so this goes to 0. It goes back to 2. Run is set to 1. This goes from 4 to 3. Still 0. This goes from 4 to 3. Still 1 because it hasn't had a chance to run yet. So, and what will run next? A? Which means that A will be reset to, run will be set to 0 when it starts to execute. And then let's look at the next one, n plus 8. This goes from 2 to 1. This goes from 3 to 2. This goes from 3 to 2. It's still 1 as it starts. Can we run now?
Yes.
Yay! It could run kind of late. That will go, I think, to the 0.8 time over here, right? I forgot C is red. Oh man, I'm really messing up in my color schemes.
You understand?
Yeah, I got it. Thank you. From here to here, this timer is counting.
All right, I'll keep going a little bit more. All right, so goes from 1 to
The timer counts down.
0. This will be set to 1 then. This gets reset to 2. 2 goes to 1, still set at 0. Oh, by the way, down here we started executing, so it goes to 0. This will be 1, 0. So what's going to start at this point in time? A. Remember, because it's round robin, it doesn't get interrupted by another task.
Okay, my question is, the time block that for n plus 10 is completely full now.
Yep, time block for n plus 10 is completely full. So we'll go a couple more, all right? By the way, this went to 0 because it started executing. So here's 1, 0. Goes from 1 to 0. Gets reset to 4. This goes from 1 to 0. Gets reset to 5. Runs 1. And it can't be actually run, so it's held over to the next one. This goes from 1 to 0. Resets to 2. Run. This goes from 4 to 3. Still supposed to run. This goes from 5 to 4. Still supposed to run. So what do we run? A. Hey, what do you know? A again.
Oh. But
Yeah, what?
B, B should have run.
Because A and B are both set to run.
But what
Yeah, it's
about
not fair. Why isn't B allowed to run? It went first.
what about right after n plus 10?
Pardon me? What about at what time?
N plus 10?
The time block for n plus 10 was full.
Yeah, during time n plus 1, A ran for the 0.2 milliseconds here, and it ran for all 1.0 milliseconds here.
Okay. And then, yeah.
So when it overlaps.
And, oh, by the way, since we're running A, this goes to 0. Well, I might as well just finish this. 2 to 1. This is still at 0. 3 goes to 1. 4 goes to 3. Still 1. So at this time, B will run.
B's timer.
By the way, it's 2, not
Two.
3.
Yeah, it goes to 2 there, sorry. So this will go down to 0 because it starts to run.
So it switches from 0 to 1.
And then this will go to 0, which then gets reset to 2. Start to run. 2 to 1. 3 to 2. It's still waiting to run. And what will run during this time? A will run.
Poor C.
So, does anybody feel sorry for task C?
Yes.
C deserves what it gets, right? That's what it gets for being low priority.
That's just probably gonna be like 1 times the C round.
So that makes all sense, right?
Include. I don't know.
So, should I give you the quiz right now?
Yeah.
All right. If you could hit the thing here. All right, we're back. We had a little bit of workshop here, so we're going to continue on. What's that for? Oh, sorry. You're just all excited about class, right? And you shake your head no. I'm glad that wasn't on camera. All right. I'm going to go through a couple more slides associated with this, and then we'll call it a semester. How about that? Except for the fun. This is a little bit more about operating systems in general. So we had a scheduler that did a run to completion. In other words, we had timer ticks between each task release. Round robin scheduler runs forever, and periodic timer triggers an ISR which updates the schedule table. So what the whole thing I'm pointing out is that at time n plus 1, n plus 2, at the beginning, right there, our algorithm says stop, go to an interrupt service routine, and start examining who needs to run now. All right, and that's what is directed and it's done in an interrupt service routine, which happens based on some periodic timer. In the first example we did, it was every 1 millisecond. In our little exercise we did, it was 0.5 milliseconds. So notice that the task execution is not interleaved with any other tasks. You've got to finish it before you can go and do anything else. Only ISRs can interrupt any task going on. And remember, the way that an interrupt service routine works is that a regular task is interrupted, you finish the ISR, it goes back to the original task. And the priority is determined by its position in a table. By the way, when you do this, you often have things like an application programming interface, that's called an API, where when you add tasks, you say literally add underscore task. You give the task name, its priority, its time period. This pretty much explains everything that goes on. You can add and remove tasks. You can identify that it's time to run this task. By the way, this is all done with a real-time scheduler. And then, of course, you can reschedule the priority of those tasks at any time you want. What's one of the problems? Well, I think we saw from this example we did that sometimes the response time is really, really long. Sometimes you may actually starve another task. We saw in the example of 0.5 milliseconds and really long running time. Nobody or no task other than A got to run. There is something called a function queue, where you allow yourself to enqueue different types of tasks based on priority. And so a schedule is made of the tasks that is not the same every single time. So I'm just going to whip through these things really fast. Now, when you buy a real-time operating system, what we call an RTOS or a kernel, is usually all the work has been done for you, and what is provided to you is some sort of mechanism to do the scheduling by saying, all right, this task has first priority, this one has second priority, this one has third priority. The assumption when you build a real-time operating system and an embedded system using it is that your tasks don't take, each individual task does not take a lot of time. The example that we showed from the book and in our little exercise, it was taking way too long. So if we had done that again, where each timer tick was maybe 2 milliseconds, and everything could run in that time no problem, would probably be more of an appropriate example of a real system. So if we look at some of the different types of scheduling that we've looked at, I've just glossed over those because we're running short of time. Round robin, all the code runs all the time. Round robin with interrupts, you can intersperse all the code tasks all the time with device A, device B, device N, interrupt service routine. Now remember, interrupts have priorities. And you can set these priorities by identifying this specific priority bit. I believe you did that in lab number 6, correct? Yes? I think you also did that in lab number 5, if I remember correctly. As opposed to having a function queue where you literally have an identified list of everything that has a priority, starting with your interrupt service routines and then your other tasks, which you attempt to run them all equally and at least a little bit more generously than round robin allowed. This will give you a nice assessment of best case and worst case. I'll kind of gloss over this. If we were to execute a round robin scheduler, very similar to the examples that we just gave, we have a couple of tasks. Specifically, here are the names of them. And it's all based on, I think I need to change my notes here, a timer tick associated with one of the timers. In the old Renaissance architecture, you had timers A, A1, A2, A3, A4, B0, and B1. You had a lot of them, actually. And in our new Renaissance processor, you have what? You have 4 of them, right? You have unit 1, you have unit 0 and unit 1. Say that again?
Yeah, timer 0, timer 1, timer 2, timer 3.
All right, so you have timer 0, 1, 2, 3. And they call them unit 0 and unit 1, right? Round robin scheduler. This will be setting up the interrupt. This is incorrect, so I'm going to go over this one. But when you're actually running the code, remember the data that we had for the round robin, the initial timer value, that was the frequency. How frequent will this run, will this specific task run based on your design of the system? You will have a integer that will identify the next time to run. Remember the design that we had here? Not that one, but this one. This will be one of the variables that you keep track of. Remember, it's decremented with every timer tick. Also, we have this one that identifies, is it time to run yet? And that is also one of the variables stored in the structure. We're assuming that all of our tasks will run, all of our tasks will be enabled so that they will run. Then we include, this is an interesting thing, it is a pointer to the task. What this does is this sets in the structure of this variable, it puts the address of the first line that executes in that function. Remember, each task is going to be some sort of function. Maybe flash this LED or go and gather this data from the pulse width modulator so that you can, or from the ADC so that you can store this data. You'll have a list of all your tasks, and then you will run the scheduler. So here's an example. If we say that we're going to use the round robin scheduler and we have 5 tasks, let's look at the example as we go through. This is the round robin scheduler code that is always running. Because it has the while one loop, this will continue to run forever. You'll usually call this from your main function. One by one, it will go through your tasks. And if the task has actually been assigned to some sort of memory location, in other words, if there actually is a function identified, this will be identified as having a real address, so it exists. Now, if it is a task that's enabled, you can check to see if it is time to run this task. And if it is time to run this task, then this is where you, remember I said you cross out the 1 and you put 0 in its place. We did this in the situations here. This 1 was then changed to 0 to be able to run. And then you will actually execute the code. So this is basically a subroutine or a function call. Notice the other thing too, then it hits break. So a break will take it out of everything and it'll go back up to here, won't it?
So there's no priority in that?
So what do you think is the priority?
There isn't. Equal.
Oh, I'm doing page down. I'm trying to do page up. Now, does this break out of this one? Or does it break out of this one?
Doesn't it break out the for loop? It breaks out the for loop.
All right, it breaks out of the for loop, so it goes back to right here. By the way, at the beginning, we just initialize everything to 0. This is the code to be able to run a task. Whenever you run a task, keep in mind that we have to identify its priority, its frequency of running, as well as, of course, the function or the address to execute that function. So in this case, you will check to make sure that the priority is in the valid range of the number of tasks that you have, and that it's not already occupied. Otherwise, then you schedule or you identify and put in the address for the task. You make sure that your run is 0. This is the frequency, so you start it at whatever the frequency is, and then of course the initial timer value is going to say what the frequency is. When it starts running, it'll start to decrement this one, and of course we're enabled. So probably the more interesting thing is in our interrupt service routine, we will go through each of the tasks, and if it is a valid task, and if it is enabled, and if the timer is non-zero, which it should always be, then you will decrement it, and that's a pre-decrement. If after the pre-decrement is equal to 0, then you set the run bit, right here, you set the run bit to 1, and then you change the initial timer value. Remember, it was at 0 because of this line, and now you change it back to 5. And this is done in the interrupt service routine, so no matter where the interrupt service routine is, as soon as you return, you will go back to running this major loop. And you will, of course, at this point probably be running right here. You will finish executing whatever it previously was, or if it was idle, it's just going through this loop. So that is the code that will be behind the round-robin example that I gave you. Oh yeah, by the way, here is, if you want to remove a task, this is basically how you're removing everything out. Enabling, disabling a task, you're just setting a single bit. Rescheduling a task, you're just changing the frequency for that. To be able to start it, again, if this is the name of the function that runs, then all you're doing is you're saying this is the frequency, this is the priority, and this is the name of the function that must execute. And then the main program, run robin scheduler, and it should never come back from that because it's a while one loop. So, that is it for today's lecture. Thank you very much. This is a continuation of lecture number 25, which I didn't get a chance to finish at the end of the semester. So I'm going to continue on talking about some general operating system concepts, and then I'll be able to go into it in a little bit more detail as we go along. So let's stay in the big picture. So we've been using foreground and background tasks. Specifically, we have things running in the background like interrupts. We also have, or I should say, things running in the foreground called interrupts because when they occur, they take place right away. And then you have other task code in the background. For example, in the situation where we had queues running with serial communications, actually handling the queues was done in the background. The foreground would be any of the characters that came in, how it was handled and put off into a buffer. The limitation, of course, is that the natural program structure is difficult to do, saying this is foreground, this is background, unless you have a higher level of control. We're going to see that a higher level of control really depends on identifying tasks that are running, and if they are not able to do everything they're supposed to do, that you set them aside and do something else that could take place. We're going to see an example of that in a second. We're also going to look at how you could share the processor amongst different types of threads or processes, and we'll define that too. So the whole goal is to share the microcontroller such that you try and use all of the resources of the microcontroller as much as possible, so that all your work gets done that you've identified for your embedded system. So let's take a simple example, our secure answering machine. In this case, and this is not unlike real answering machines, you have several parts associated with your answering machine, and in fact, let's take a look at this. Of course, central to all of this is the microcontroller itself. And the microcontroller will have different interfaces. It will show you things like a number of messages waiting for you to record. It'll take input associated with user keys, go forward, go backwards, whatever. It will have, excuse me, the telephone line interface. It will also have its own memory so that it could store any messages that come in. It has speakers and amplifiers and such. So take a look at, if we were to use round robin, which we've looked at in quite a bit of detail, and you think about our answering machine, there are several things that are going on. Store the encrypted voice messages in some sort of non-volatile memory. If you want to delete messages, you have to take care of that, and then you also have a user interface. So with all those applications, you can go through and say, all right, in the function called delete the message, so you've identified that there's one message you would like to delete. You display on the LCD, are you sure? And it takes about 10 milliseconds for that to run. Then you need to debounce the switch, yes or no. So if you have debounced the switch and you get the input, then what you will do is look at that, and if you decide that you want to cancel the deletion, then you will do that. If you want to actually delete, then you have to work with the flash memory in your microcontroller system. Now, flash memory, I've described this in the past, it often takes quite a bit of time to actually go out to the flash memory. You write entire blocks out to the flash memory, and to delete, you need to do something very similar to that as well. It might take anywhere between 250 milliseconds or 250 microseconds to even more, even 20 milliseconds or so, to be able to read from and then write back to that flash memory. This is all taking time. And in fact, there are some other things that are taking quite a bit of time too. That wouldn't it be nice if you could do several things at one time, and while some very slow peripheral out there is working, then you can go off and do some other processing. So that's the whole premise and the whole idea when we're talking about running our answering machine application. So let's take a look. Round robin, run to completion. You do everything methodically. You do this, then this, then this, then this. In our example right here on the screen, you see that you will display here to the LCD, are you sure? You will wait a very long time, and depending on that, either you display cancel or things time out, or you do things one at a time, which may take an awfully long time. So maybe a better way to do this is similar to what we've seen in the past, and that would be with a state machine. So we have, let's say, 13 different tasks and use a state machine to design that. So let's take a look at a state machine. Are you sure? And then state number 2, depending on, well, you wait for the LCD to actually display things on the screen. Then you wait for the debounce switch, and that's going to take an awful long time. Depends on what the debounce says, display of the things, etc., etc. By the way, there would be several other states going that way as well. So, the thing to take a look at is that there are some functions that are relatively slow, some that are fast. So again, the LCD is slow. Data flash is also a bit slow if you want to write to it. And oh, by the way, switch debouncing is really a physical characteristic of the mechanics associated with that switch. So those slow functions really depend on a peripheral. Wouldn't it be nice to make those slow functions give up the processor? In other words, not have us poll, but give up the processor, and when that peripheral is done, come back and say, all right, I'm done, let's go on to the next task. And that may be needed if you have a very complex system. By the way, when you do this, it opens up for a new species of bugs because there are all sorts of different processes that could be running that are using the processor. So let's take a look at what we would do. What you need is something like a kernel. And this is no, not a military person. All right, go ahead. Laugh, yes. A kernel, K-E-R-N-E-L, which is a central part of an operating system that will share the single processor that most microcontroller embedded system devices have. And it will share the processor amongst multiple concurrent running tasks, threads, processes. We'll define those in a moment. This kernel will also be in charge of that microcontroller as a resource, and it will forcibly switch between these different threads or these different tasks, processes, whatever are running. It is the heart of the operating system. There are some kernels that are relatively small, there are some that are relatively large. So in our kernel mode, the kernel itself is in what we call supervisor mode of the microcontroller. It's really the operating system, and it's not user code that's running. So, if we're looking at a perspective of an embedded system versus an operating system, you have to keep in mind that in a PC, in a workstation, you have to worry about things like a file system. You might be working with a lot of different files, a lot of different applications. And so your operating system will handle everything from the process that is running, synchronization, memory management, because if you have one program running like Microsoft Word, you really don't want it to run and use the data over here in Microsoft Excel unless you run another process that physically copies from here and pastes to there. But you don't want them working with each other's program or data memory. You also have to worry about time management, I/O devices. In other words, an operating system for a PC and a workstation is rather complex because there's a lot of different things that go on. Now for an embedded system, mostly what you're worrying about is how do I share the processor? Very infrequently does an embedded system have a file system. I'll give you a good example. If I am running my stove, and I've shown the embedded board that came with my stove, that will not have a file system because I'm not reading to and writing from that device. It is running, it may have some global variables, but it's not really sharing files between different types of I/O devices. In fact, if you think about it, the only I/O devices themselves are the keypad and the display. So in an embedded system, you're really worried mostly about thread management, in other words, sharing the processor. Now, we did not go in this class as much into the use of concepts like stack and heaps and where the global data actually exists, and also what a lot of the registers mean, but you should have a good idea of that from your earlier computer architecture courses. So for us, we're going to look at the following just as a general concept. We're going to say that a program process thread is going to have information about its running state. Think about the programs you've written for labs. You had global data, you might have had some temporary storage on the heap, you might have actually the program itself has instructions. And which instruction you're running is pointed to by the program counter. Remember that? Well, now imagine we have several of these entities, these processes, these threads running at one time. Each one could run independently, and each one will have its own stack, its own set of instructions, and its own global data. Now, it may be that this global data can be shared between these processes, and we'll look at that in a later class. So we're going to have all of this information associated with a single program processor thread. By the way, what is the definition? If you have a process, that means that no information is visible to any other process that is running. So nothing is shared. You can't share information with each other by using some sort of operating system mechanism. We'll see a little bit later on what those mechanisms could be. A thread, on the other hand, shares address space and code with other threads. Now the big side effect, of course, is what we call context switching. If you're switching from one of these processes to another process, you have to save off a lot of information. But switching between two threads means that you're swapping a lot less information. And very often what you'll have is one thread calling another thread, and when that thread is done, it returns, almost like a subroutine. So, here we have, as we said, let's say two different threads that are running. What we'll do is we will create what's called a thread control block, or a TCB, which will store all the useful information. This defines a lot of the useful information that we need to work with. Temporary registers, the address registers, stack pointers, as well as the program counter and copies of flags that might be running at one time. Now imagine this, if you're running thread A and you want to switch to thread B, remember our microcontroller really only has one set of registers that you could use. And so all the registers that are important to thread A need to be saved. And then when thread B runs, it has its own set of registers that it needs to run with. So we have this wonderful situation where we have a different stack for A and B and a different set of instructions or program for A and B. And it could be that we use the same global data. What we'll see is a situation where we have a single task or a single thread, A, that is currently running in the CPU. And the operating system says, hey, task A, it's time for you to finish your current instruction. Then we're going to give control to task or thread B, so it will run, and so it will have a chance to use the microcontroller. Again, microcontroller, there's only one. So what will happen is that the CPU running task A will have to save off all the information from the CPU to some area in memory. Usually it's in on the stack, sometimes it's in global memory, that will have a copy of everything that was in the CPU. All the registers that were in the CPU will be copied over to TCB-A, that part of memory. The next thing that will happen is that the previous saved configuration for task B, which is pointing to a different area, will then be written into the CPU, and then task B or thread B will start to run. So all that data will be copied over from memory into the CPU registers, and of course, as soon as you put a new address of a program in the program counter, it'll immediately start to execute that program. Now, how does this happen? In an operating system, you typically have different states associated with all the different threads and processes that are running. When you first create a new thread, you can, of course, identify all the important information about it, including where it's going to store its thread control block. Then it is put into a state which is ready, meaning that the process or the thread is ready to go, but remember, there's only one process or thread that could run at any one time, because you have one microcontroller, and the microcontroller is that entity that runs the code. And so you could have several queued up, ready to run, and as soon as it is the highest priority task, thread, or process that needs to run, then the device, or I should say the operating system, will move a thread or a process over to the ready, or it may move it over to the waiting. Again, the waiting state is going to be that a particular thread is waiting for some event to occur. That could be the availability of a resource. Maybe it's waiting for a keystroke from the keyboard. You could also have terminated threads, and of course, if you're looking at this, you could have multiple threads in this waiting state, multiple in this ready state, obviously multiple in new, and multiple in terminated. As you can imagine, a thread will not stay in the new and terminated states very long. Most of the time, all of the threads are running or are in one of the states of ready, running, and waiting. And that's shown here. You will have specific queues associated with waiting and ready. And in fact, often what we do is we create a priority queue in the ready state, meaning that that thread that has the most important task to complete will be moved into the running. I've mentioned this example before. Maybe a ready task or a ready thread is going to be, there's a phone call coming in on your cell phone, answer the phone. And so that would be moved to the running state, and maybe whatever was running will be moved off to something that's a little bit later, or be moved off to waiting or to ready. So again, the operating system, to keep track of everything, needs to keep a queue associated with, oh, I've got these 7 tasks or these 7 threads that are in the waiting state, and I've got these 5 that are in the ready state, and of course there's only 1 that's in the running state. So who moves these threads between the different 3 states or the different 5 states? The answer is the operating system, usually the kernel, is that entity which will do that. As an example, if we have here a data structure, we'll have maybe 1 new, 3 of them are ready, and 3 of them are waiting, and of course there's only 1 that is running. What we will use is what we call doubly linked lists. We've seen this before. The thread control block or the task control block, again, we're storing all the registers. This is the important information that is associated with the microcontroller. Then it will also have a pointer to the next task control block, and it also has one to the previous one. Since it's a doubly linked list, it's easy to pull one of these thread control blocks out and move it over here into the running state, and then you can just join this one back up with that one. And in fact, one of the examples that I show here is just that. If we have what's called a context switch, in other words, one thread is running, thread A, and we decided that we want to run thread C instead. What we would do is we would copy off the contents of the register in the CPU off to the thread control block. We would add that specific thread control block to the ready queue. Then we would take C, and that would be added to the, we put TCB A to the ready queue. Then we would put C into the running queue, which of course only has one, and then we copy all the contents of that thread control block into the CPU, and then that task will start to run. All right, well that is all we have. Lecture number 26 is going to go into a little bit more detail about operating systems, specifically how do we share data, and how do we do stuff like ensure that we don't have deadlocks, or that we only run the correct process at one time. Thank you very much.